Well, thank you so much, Leon, for that great introduction. And as was mentioned, my name is Brendan Smith. I'm a current postdoc here at MIT in the Material Science Department, and I work with Professor Jeffrey Grossman. I'm really excited to be here today to share with you about 5 years of work really centered around the development of our main technology, which is this durable silica filtration membrane for low cost, low energy industrial separations. So why do we care about this technology and problem that we're working on? Well, about 5 years ago, we started to try to answer the question, how can we make today's mega industries more sustainable, both in terms of financial cost, but also energy and resource cost? I think it's no secret to the audience here today that industries like textiles, oil and gas, and chemical production, among many others, are consuming vast amounts of resources, chiefly energy and water. What might surprise you, though, is that 10% of all global energy use is actually encompassed simply in the industrial separation stage of these sectors, among many others, of course. And the industrial separation piece is really just taking complex liquid mixtures and separating them into diverse pure components, for instance. And taking a deeper look at this, the reason it's so energy inefficient today is about 80% of these separations are performed using thermal processes like thermal distillation, whereby we take these liquid mixtures and essentially inject huge amounts of thermal energy and boil off different components at different temperatures and pressures. This works well, but it's actually widely known at this point today that we can, by transitioning to a more energy efficient separation approach, like membrane filtration, for instance, we can consume about 10 times less energy and achieve a very similar result in most, if not all cases. So the follow-on question then is, why aren't we doing this today? And to answer this, we have to take a hard look at the membrane technology landscape, where on one hand, we have polymeric membranes. These really dominate the industry and are relatively scalable and low cost. They also offer excellent nanoscale selectivity down in that nanometer range. But where they struggle is in their chemical and thermal fragility, which makes them ill-adapted for many industrial separation processes due to the harsh environments that are involved there. So what you can do actually is go to the other end of the spectrum, which is the ceramic membrane technology, like silicon carbide or titania, which gives you ultra-high chemical and thermal durability. But where these fall short quite often is the lack of nanoscale selectivity. So these technologies actually can't address constituents like divalent ions or small molecules, which are extremely prevalent across many industrial environments. Ceramics are also quite expensive from a capital cost perspective, but that cost can be relatively smoothed out over time based on the longer life cycle and lower maintenance cycle requirements relative to polymer. So when we tried to set out to invent a new technology to really plug this gap or fill this gap in the landscape, we decided to start from scratch and source low cost and durable materials. In our case, we selected silicon for a number of reasons, and then developed a scalable manufacturing process, which we've now patented through MIT. The process itself is quite simple and really only two steps in its entirety. The first is to deposit a metal catalyst onto the silicon tile surface, and the second and final step is simply to immerse that entire silicon tile into a chemical etch bath, which then facilitates passively the selective oxidation and removal of the silicon from one side of the tile to the other, to really form these long, porous channels that allow the flow of fluid to pass through this tile. So looking more closely at the surface, we can see in dark contrast here in the larger image, the pores actually opening up. And looking even more closely, we can see we're actually able to produce these pores with diameters less than 5 nanometers across, which is relatively unique in the inorganic membrane or durable membrane space. But the real magic happens in the cross section. If we cut the material in half and look from top to bottom, again we can see these nanopores running in dark contrast in these straight lines. And by virtue of their diameter and also their chemical character, they act to allow the flow of water or other important industrial liquid while blocking out or restraining important solutes like waste products or chemical products that you might want to concentrate in your industrial process. So speaking of industrial processes, we've explored quite a few over the last few years, one being the textiles industry, where we can take textiles wastewater or effluent and through a single pass through our membrane, actually remove these sub 1 nanometer dye molecules and extract almost pure water, as you can see on the slide. This pure water can be recycled back into the textile dyeing process, saving both water, energy, and cost in this application. On the other end, we're also looking at the oil and gas industry here in the US, and chiefly focused on the treatment and recycling of produced water, as you can see here by taking these heavily loaded oil water emulsions and extracting almost pure water, which can then also be recycled back into the hydraulic fracturing process. And we're also able to recover the solid hydrocarbon product in this case, and then clean the membrane to rejuvenate the performance over relatively short cycles. So by talking to really hundreds of customers over the last few years, we've really been able to tease out and parse out the important pain points and specs that they require us to provide in their operations. So not only do we need to provide these intrinsically good materials properties that we find in our silicon material in terms of thermal, chemical, and physical resilience, we also need to provide a suitable filtration performance. And so today we can reject molecules as small as 150 Daltons and provide permeabilities anywhere from 1 to 10 LMH bar, depending on the application, numbers that we're pushing better and better every month. But of course, the economics are also crucial here, especially in a business-to-business type of market. And looking at some extensive techno-economic modeling and actually working with manufacturers in the area, we've been able to predict that at scale, we can actually produce our technology for 5 to 10 times less than the cost of the closest ceramic competitor, which gives us confidence we can penetrate into these large markets. So just to wrap up a couple of examples that we're looking at, in the textiles effluent treatment industry, as I mentioned, there's a huge demand for this kind of technology. And this really stems from the annual treatment costs of over $2 million faced by an average small mill in a place like southern India. And actually working with these future customers, we've come to realize we can provide a reduction in this operating cost up to about 60% on an annual basis, at the same time reducing the water and greenhouse gas emissions at almost about 1 trillion liters per year and 500 megatons of CO2 per year in this market alone. On the other end, in produced water recycling, a very similar pain point where operators are facing this increased cost of transporting water from the wellhead to the injection well or centralized treatment facility, over $10 per barrel in some locations. But again, by working with these operators, we've come to predict we can reduce this cost by about 70% by treating and recycling water on site, thereby reducing water usage by about 1 billion liters per year in the US alone. To close with some really exciting news, we're actually spinning out of MIT this summer as a company with my co-founder, Jeffrey Grossman, and we're actively seeking opportunities for investment and partnerships in all these different industries. And so if you're interested in this, please come join me in the breakout room at the end of the session. I'd love to talk more about it. And with that, I'd like to thank our sponsors, first and foremost, the MIT Deshpande Center, as well as the others listed on this slide. And I'd like to thank you all very much for your attention.